So the first speaker for today is Carlangelo Liverani, which is very welcome to be here, and he will from the University of Roma Tor Vergata. You all know him very well, and he will talk about asymptotic properties of deterministic fast-slow systems.
It's a pleasure to be here, especially because I kind of like this fact that there is a dynamical community that is growing in Italy. I mean, when I came back to Italy from the United States, the dynamical community in Italy was rather small, and it felt a little bit lonely. And I'm really happy that, you know, well, okay, these are just remembrance of an old guy, forget it. But it's nice to see that there start to be quite a few people in Italy and that work in dynamics, and the fact that there are so many international connections as well. So as far as the talk is concerned, well, I am afraid some people in the audience heard this talk more or less already, because I'm working on this stuff for some time now, and to be completely honest with you, in the last year or so, I've been remarkably unsuccessful in making any progress, so that means that what I'm going to talk about is not changed much since more than 1 year. But nevertheless, maybe there are young people, maybe they never heard it, so okay. The other one, maybe they have some email to do or something. So, all right. So let me see if I understand how this works. No? This, yes. Okay, so what's averaging? Averaging happens in many different contexts. So this is a very simple example in which you can have average situation. You have essentially two different scales in time in this case. There are some variables that evolve in time scale 1, and there are some variables that evolve much faster at the time scale epsilon minus 1. And the idea is that you would like to know what happened to the slow variable for reasonably long times. And so here is the idea is that in first approximation, the slow variable will see only the average motion of the fast one. So a very simple example, bordering on the stupid, is this one in which, that's funny. Okay, in which you have a vector field which is just constant, okay? So this is the vector field of, maybe you should, can I go back? Yes. This is the vector field, the W is the vector field of the fast variable. X is the fast variable, Z is the slow one, right? So in this case, the vector field of the fast variable is just constant, and it is in 2 dimensions, and it is a vector which has a rational, irrational slope. So as a consequence, you know, you have a motion on the torus that is just a translation by an irrational number, and so it is ergodic. So the invariant measure is Lebesgue. It happens to be the unique invariant measure. And so in this situation, you can prove, indeed, that if you look at the slow variable, this will converge to some ODE, in which the fast variable has disappeared, and the vector field will be just the average with respect to the invariant measure, which is the Lebesgue of the vector field that you had for the fast variable. So this is, okay, a very kind of nice situation. And there are 2 reasons why this example is exceedingly simple. One reason is that the fast dynamics does not depend on the slow one, because in this case it's even constant. And the other thing is that the fast dynamic is uniquely ergodic. So there is only one invariant measure that matters. So these 2 things are in part, of course, related, because you can do this very minimal sophistication just to have always a constant vector field, but now it depends it depends from the slope variable. And then, of course, if this varies continuously, then you will have resonances. That is situation in which the ratio of the two components of the vector field of U1 dependency is rational. And that means that the trajectory will be periodic. Every trajectory will be periodic. And on every trajectory, you can put an invariant measure. So you have uncountably many invariant measures now. And these are called resonances when you have such a situation in which the ratio between the two components of the velocity are rational. And when you are resonance, this is a well-known problem in this, in this type of situation. And okay, and the more in general, if you have a vector field on the other end that still does not depend on the fast variable, but it has more than one invariant measure, then still you have averaging. But now the problem is that you don't know which measure you have to use in order to do the averaging. And which measure you have to use, it will depend essentially from the initial condition. If you start with an initial condition that is typical for the measure mu I, then the average will be with respect to the measure mu I. So now you have an extra complication that the initial condition will matter. So in some sense, an all kind of possibilities opens, and of course, a general theory is not really available. But there are two cases that are reasonably understood. One is regular motion, for example, in a Hamiltonian system, when you have an integrable Hamiltonian system, and then you can say quite a few things, especially in celestial mechanics. There are a lot of applications of fast-slow variable. And the other situation is when the fast motion is chaotic, for example, typically in a Nosov system. And what I will discuss in this lecture is exactly the latter case. Okay, very well. So that is what I would like to talk about. So, all right, so the problem is that like that, it doesn't really have much hope, right? It's too general of a problem. So if one would like to do something, one has to make some simplification. So what I'm going to assume is that the fast motion, so the fast motion in general will depend on the slow variable, which I call z here. But you can imagine that you freeze the slow variable and then you look at what happened to the fast motion, right? And if you do so, I ask that there is a unique relevant measure somewhat. Call it SRB, call it physical. They are more or less the same, but there are subtleties that I don't want to enter in. So that means that there is only one invariant measure, which would be mu of, I call it mu of z, and this invariant measure mixes exponentially fast. The fact that this exponential is not relevant, but it has to mix fast enough, let's say, right? So that is something, because if this is not the case, then again, it will depend from the initial condition. Situation will become much more complicated, and I don't want to enter in that. So what does it mean in concrete? In concrete, this means that if I start with an initial distribution for the fast variable, which is absolutely continuous with respect to Lebesgue, and it has some regularity, so you know this m is the distribution of the fast variable at time 0, and the Raton-Nicolin derivative with respect to Lebesgue, I call it h. I assume it to be at least C1. And then you look at the evolution. At frozen, this is the evolution when z is fixed, okay? So then there is what happens. It happens that you look at the average of some function at time epsilon t. So yes, epsilon t, because this one I should go back. Well, whatever. If you recall the vector field of the fast variable had epsilon minus 1 in front. So epsilon t is the time at which something happens, things move over the 1, essentially, right? So if you look at time epsilon t, then, and you compare it with the average with respect to the invariant measure, this difference goes to 0 exponentially fast. And here, this is important. There is a constant, and then there is the C1, norm of phi and h. So this is drastically different from, there are fast slow also, for example, in random processes, right? You can have a Markov chain, and it has a component that is fast and a component that is slow. You can do similar things. But there, typically, Markov chains, they have decay of correlation of this type. So something like this happens again. But here, instead of having the C1 norm, you have maybe the L2 norm or some Sobolev norm. So you may think, who cares? Well, it is annoying from the technical point of view. It makes your life rather miserable in many ways. But that is what it is. I mean, that is, it's not that one cannot prove, is that if you put the L2 norm here, then this will go to 0, but the speed at which it goes to 0 can be arbitrarily slow. Okay, very well. So this is life. And so now I want to consider the initial condition for my system, and the initial condition will be of this type. You see, if I take, this is the expectation, means expectation with respect to the initial condition at time 0, and it will be exactly the following. So the slow variable is essentially a delta function. I can tell you exactly what is the initial value of the slow variable. In this case, it is z0. But the fast variable, it is just distributing according to this measure m that has this property. So the idea is that the fast variable moves very fast, and you do not know really where it is. You just know some distribution of the fast variable, but the slow variable, you know exactly where it starts from. And that is the setting that I would like to understand and discuss. Okay. And what you expect? Well, you expect exactly the same as before. The slow variable, when epsilon goes to infinity, will converge to some effective equation in which the fast variable has disappeared. And this vector field will be the vector field of the slow variable averaged with respect to the invariant measure, where the same parameter z here. Okay, and that is the formula for this effective vector field. So the idea is just that, as you saw before, this happens very fast, right? Because if I look at time 1, so that means that t is yeah, I'm afraid this is t over epsilon, right? Yes, yes, this is epsilon minus 1. I'm sorry. This is epsilon minus 1. Yeah, apologies, yes. And the point is that yeah, but you see, there are choices to be made, right? And I'm afraid I made the choice already. And the choice that I made was this one, right? So it means that when t is equal 1, epsilon, the fast variable, has moved quite a bit, because the speed of the fast variable is epsilon minus 1. So that means that so that means that is okay, actually, right? Yeah, because this t here is not the t that, I mean, that's bad notation, let's say, right? This is not the t, this epsilon t is what I would like to call t, right? Because that is the time. So when this quantity is of order 1, this t here is of order epsilon minus 1, and this is incredibly small, right? This is e to the minus c epsilon minus 1, essentially. So that means that very, very quickly the system, the fast variable is in equilibrium. And the slow variable changes so slowly that sees always the fast variable being in equilibrium. And so always see its average, never its actual position. And so that's why the behavior of the fast variable depends only on the average of the vector field. Okay, so that is standard averaging theory. I mean, I will say more later on, but that is what it is. And let me remark that it's kind of interesting that this equation, if you enter now in the room and you look at this equation, you think, well, this guy is talking about autonomous ODE. I mean, some autonomous system of some variable z, and that's it. Okay, but in fact, this is not really an isolated system, as we have seen. This is just a description of a small part of a larger system. And in fact, this is what happened in reality, right? I mean, all what these systems that we call isolated, in fact, they are always effective theory from a larger system, because everything really interacts with everything, right? I mean, so that is what physicists do at all level, and they call it actually renormalization normally. I mean, but this is average. It's more or less the same thing, right? If you go to a place in which physics talk about quantum field theory, they will talk about effective theories. It's more or less the same. They just average on the smaller degree of freedom, the faster degree of freedom. So the idea is more or less ubiquitous in mathematics and in physics. Okay? Okay, fine. So the system is not isolated. Can I see that the system is not isolated, that in fact is interacting with other things? Well, I mean, if I want a more precise description, which is needed in many situations, then one can do two things. So can look at smaller scales, just look closer to see if really the situation looks like a normal ODE or there is some correction, or you can look at longer time scales to see that looking at the system for a very long time, one sees a deviation from this effective equation. So, so there are partial results in this direction, and that is what I would like to talk about, because the applications that I have in mind actually require, in my case, longer time scales. But these two aspects are kind of very much related one with the other. Okay, so fine. The problem is that it's not even completely clear. I mean, you want to go beyond averaging, essentially. This is my goal. But a priori, it's not super clear what is the question that you have to ask, essentially. What do you want to do? So to this end, it is better to, at least for me, to look at concrete example. I mean, personally, that's my way of thinking. I mean, when I start to do the general thing, I get immediately confused. So if I have a concrete example to study, then at least I know what I have to do. I mean, I'm a very concrete human being. So, of course, if I want to study a concrete example, then it's better to start with some simplification, right? Because you don't want to start from the most complicated situation. So that is, I want to make some simplification of the situation, and here is a bunch of way of simplifying the problem. So first of all, consider discrete time, a map rather than flow. It's not, okay, just make life slightly easier. Consider as few degree of freedom as possible. That means two, one fast and one slow. And realize the complex dynamics in the simplest possible way, maybe an expanding map. This is not much simpler than that. And then, you see, what I'm interested in is application to Hamiltonian systems. Hamiltonian system, typically, the problem is that if you have a large Hamiltonian system, then of course the energy is conserved. So everything happens in a compact space, but the size of the compact space grows with the number of degree of freedom. So in principle, maybe you would want to look at problem in non-compact spaces, but I just restrict myself to the compact case. So if you just, I mean, these are all reasonable, I think, simplifying hypotheses. If you try to simplify even further, then you get to a situation in which the problem becomes trivial, and so it's not so interesting, right? So that is, if you do this simplifying hypothesis, then essentially you end up with this problem. That what happened to you. So what is this problem? This problem is just a map from the two torus to the two torus. So you see, I mean, I started with some ODE, very general. Now I'm really being humble and looking at the simplest possible situation. And the simplest possible situation, you see, looks like this. This is x is still the fast variable. Now, I mean, I changed, right? Because you see, I just to add to the confusion, now the time 1 corresponds to the fast variable, and the time and the slow variable move at speed epsilon. So now this is rescaled with respect to the previous one, but in a moment I will rescale it again and go back to the time that I used before. I'm sorry, the problem is that, see, you have two different time scales, right? One is fast, one is slow. And now you have to give a name to them. And of course, you keep, I mean, that's happened to me. I keep changing names. So one time I'm working in, I call the fast one the microscopic scale, and the slow one the macroscopic scale. So this is due to the fact that I have in mind some picture in which the microscopic one corresponds to something very small that move, and the macroscopic correspond to something that is maybe, I know, the pressure, but of course I am so far away from this ideal goal that I have in mind that it's ridiculous to, but still I call them in this way. Okay, so this is the situation here. I have the fast variable and the slow variable. You see the slow variable at each unit of time changes only by epsilon, and while this one changes by order 1. And the dynamics, of course, is given by the iteration of this map. The initial condition is exactly as I said before. The fast variable can have a specific value that, just to confuse you any further, here I call z bar instead of z naught. Don't ask me why. I mean, it's just, and instead the density of the distribution of the fast variable, instead of calling it h, I call it rho. As you see, I'm really persistent in changing notation, I'm sorry. And the dynamics at fixed z, it is expanding in the sense that if you take the derivative with respect to x, then this is strictly bigger than 1. And you see, if epsilon is equal to 0, then z is conserved, right? So you have a conserved quantity. Conserved quantity, this is a trivial conserved quantity, but it's important. If you think about system like Hamiltonian system, then, or statistical mechanics, this is my end goal, then conserved quantity are the bread and butter of statistical mechanics. So it's something important to have something that looks like a conserved quantity. And rho, I take it C infinity just because, I mean, C1 is okay, but no, actually, C1 is not okay. Maybe I need to do what I need, I think, C4, but doesn't matter. C infinity is perfectly okay. Okay, let's go on. This is my fault that it has this background noise, or no, I don't know. Maybe I'm touching something. Okay, so what is known about this system? Well, if you fix z, at z fixed, so this is a map for each z, is an expanding map. So it's known since the work of Ruel that it has a unique measure that is absolutely continuous with respect to Lebesgue. I call it mu z. So the density, I call it rho star, and is a function that in fact is C infinity, both in x and in z, meaning that if you change a little bit z, the density changes off just slightly. So this is what is called the linear response, if you want. This is a further version of linear response because you have a lot of derivative, if you want. And also, if you fix z, the dynamics has exponential decay of correlation. So this is a very, very simple system, but it has all the characteristics that I hope to have ideally in a more complicated system. So if I am not able to study this system, which in fact I'm really not, then there is not much point of looking at more sophisticated situation. Okay, so let's see what I can do for this type of problem. So first of all, I want to accelerate the system. So I want to look at a time in which the variable, this variable, changes of order 1. I'm not doing anything now, so I don't know. Maybe it's not my fault. So you see, the dynamics is simply the sum of these, let's call them jump at time k. And since this is a bounded function, in order to have this of order 1, I have to wait a time of n of order epsilon minus 1. So it's kind of normal to look at, introduce the variable z epsilon of t, which is epsilon minus 1t. Okay, so that means that when this is 1, this is z of epsilon minus 1, so this quantity is of order 1, hopefully. I mean. So this is just, now this t here is exactly the t that I had at the beginning, because when it is of order 1, the slow variable changes of size 1. Okay. And okay, so this this part here is just to make is just this picture, right? To make it continuous. This is just because I prefer to work with continuous function. Otherwise, I could work with piecewise discontinuous function, but then I would have to use the sort of topology, which I never learned to spell. So this is much better for me. So okay. So I can use a continuous function. And since the initial condition is random, so is the path, okay? Because the path of the slow variable will depend on the initial condition of the fast variable. And since the initial condition of the fast variable is random, so it will be the path. So I can interpret the epsilon as a random variable in C0t. And if I do that, then indeed it's possible to show that it has accumulation points just because it's uniformly Lipschitz. So it's actually obvious that it has accumulation points. And the accumulation point satisfies this ODE, which is what I was talking about. There is a vector field that now I call omega bar, just again to change notation again, so I keep you on your feet. And this omega bar is obtained by taking the average of the jumps that are at each time with respect to the invariant measure with respect to the same parameter z. Okay, very well. So this equation now, since omega bar, this guy, I said, this is a smooth function and this is a smooth function, so this is a smooth function, so this differential equation has a unique solution. And so it means that all the accumulation points must satisfy the same differential equation with the same initial condition, so there is a limit. And the limit is just the solution of this ODE. Okay, so this is averaging, oops, wrong. And this actually goes back to Anosov in the 60s. And there are now quite a few new theories, especially due to Dolgopiat and Kelly and Merkburg, new way of approaching this problem that allow to obtain sharper results. Okay. But the thing that I don't like about this result is the following. Let me go back. So the thing that annoys me to no end is this one. Okay. This you converge, but for a fixed time. T, capital T, is arbitrary, but is finite. It does not depend on epsilon. So it means that if you want to see something that is when epsilon goes to 0, in the time in which you want to control the process grows with epsilon, which is what essentially I need for the application to statistical mechanics that I have in mind, then this result is rather useless, unfortunately. Okay, so that is the first question that I would like to address. The fact that I would like to go to longer times. So how do I do longer times? To go to longer time, I have to worry about the fact that maybe the ODE that I was looking at, which was this one, maybe is not really the right equation. Maybe there is a small correction, because after all, these kicks that the particle gets, I can imagine that they are kind of random, but if they are kind of random, then probably, since they are the sum of epsilon minus 1 random variable, maybe they will be of size square root of epsilon, if something like the CLT holds. So there is a hope that maybe this equation is better at describing the slow variable. So this part here is just the ODE, averaging ODE, and this part is this is a Brownian motion of size square root of epsilon with some diffusion coefficient that I have to compute. So this type of equation were introduced by Hasselmann in 76, sorry, and he recently got the Nobel Prize just for his work. They were introduced in atmospheric climate studies. Okay, and they were studied to the death by Wenzel, Friedel, and Kiefer in the 70s and in the 80s. So, okay, people understand quite well what happened to the solution of these ODEs, so SDE. And so one would like to understand if this is any better. But to understand if it is any better, it means that I hope that the true dynamics is close to the solution of this stochastic dynamics. And the question is that what the hell this close mean? I want to know exactly what it means. So, okay, so this was my first exercise when I started to work on this subject. So the result was obtained together with Desimoy, and then there is another paper with Desimoy, work, and Poquet, in which we actually, putting these two papers together, we obtained this result that says that indeed the slow dynamics, this is the true slow dynamics, the deterministic one, is close to the solution of the stochastic differential equation by these two different by more than epsilon with the probability that is small, epsilon to the alpha. Alpha is more or less, not quite 1/2, but almost 1/2. I mean. So, and the time is also epsilon to the minus alpha. So these are close for a rather long time, like 1 over square root of epsilon, maybe. Not quite, because at square root of epsilon, some correction should kick in, we believe, but we haven't been able to prove it, actually. Okay, so this is a result. I don't enter in the technicality to prove this result, because, okay, so this is a source of unhappiness for me, because the proof is essentially brute force. I mean, in the sense that you just do a huge amount of computation, so there are at least 200 pages of computation, and at the end you get the result. But there should be a smarter way to do it. I haven't found it yet, but okay.
Can I ask? So
Yes?
we need two epsilons here. So one is the slow fast epsilon.
It's the same.
The other is the difference being better. So you could say what is the difference greater than delta, say? So
Well, I mean, the point is that, so if here you put delta, then, no, here you want to put delta, right? But the point is that, yeah, but still, I don't know.
is just is the right hand side can you say more on different
Maybe, because if you put delta, then it will be, maybe you can say more, because the correction is the second correction, essentially is an edgeworth expansion for the CLT. So the second correction will be of order 1 over n, so that is should appear, I mean, but if you ask to be just bigger than delta, that is kind of, when epsilon goes to 0, that is huge for,
yeah, and delta goes.
you want that to,
For more uniform.
yeah, maybe, But the point is that the estimates that we have, they tend to collapse if we go to time longer than this one. If we go to time longer than this, I mean, this one is just say that this is small. This alpha is not really the same alpha. I just put it the same alpha for convenience in presentation. But the key problem is this one, right? If you want to go for time longer than this, then we lose control, essentially. Because we have to compute it. There is a term that appears that we just say is small and we throw it away, but now you have to know exactly what it is. So then this you can put here some delta, and that would be, but the problem is that, you see, you may want to restart, right? So what is useful here? You can control a time that is of this size, and then at the end, maybe you want to restart. If you want to restart, you have to know what is the difference, you know, with, so this allows you to restart a little bit, not so much, but a little bit. But in any case, I mean, yeah. Sorry, the answer maybe is not very clear, but the problem is that, you see, this is 18, so I forgot actually some detail. Yeah. But yeah, you can do a little bit better, but not much. I mean, maybe if you work much more, you can do better, but okay, yeah.
Can you say anything about the probability of the supremum being bigger than or equal to epsilon?
So this is at fixed time, right? Yeah, this is an estimate at fixed time. Yeah, you can say something about the supremum, yes, but I don't remember exactly what. I mean, because yeah, I think you can, because you can use. Yeah, it's like what is this Burke something inequality? I never remember what the hell it is. I mean, yeah, you can say something, but I don't remember exactly. Yeah, yeah. The point is that you know that this guy is, you know something about the regularity of this guy. So with this estimate, you can say something. But I don't remember exactly the exact estimate that you get. I think we wrote something about that. So you want to see that the process are really, the trajectory are really close. Yeah? Dimitri?
It's important alpha is how it's related to 1/2, I think. This alpha.
Alpha is close to 1/2, but we cannot quite get to 1/2.
Because you see your noise actually is the square root of epsilon close to process without noise.
Yeah.
And I cannot figure out if alpha is smaller than 1/2 or larger than 1/2, one of them is just, it makes result useless, you see. Because you compare the average.
No. The typical, for example, the difference between this guy and the solution of the ODE is of order of square root of epsilon. Okay.
That's what I mean.
Yes. So yeah, but here there is epsilon, right? So if yes, so it means that this mistake is much smaller than the difference between. You see actually the fluctuation here, right? Yeah. So this epsilon to the, this is just that, this say that the probability is small for a time that is very long. And the fluctuation that you control is much smaller than the difference with the ODE, right? Okay. So, okay. So now, what can you do with this result? Oh, sorry. What can you do with this result? Well, you can do certain things and not other. It depends quite a lot from this guy here, right? Because imagine that this vector field for example, has only 1 0. Well, no, it cannot have only 1 0. It has 2 zeros. That's the minimum. Either there's no zeros, that means that it just rotates, the slow variable rotates. But imagine that it has 2 zeros, one stable and one unstable, okay? Then it means that this, if you forget the random part, this guy will just have 2 invariant measures, one on each fixed point. One will be attracting, the other one will be repelling. And when you add the noise, the repelling will be unstable, so it will disappear. And then you will have only one invariant measure, which is concentrated nearby the attracting fixed point of the vector field. Okay, so there is a 0. This vector field has a 0, and this is a fixed point for the solution of this ODE. And it will be essentially more or less a Gaussian of spread the square root of epsilon. That's what you expect. Okay. And now, what will happen to the solution? I start with some initial condition. What will happen? It will happen that in an exponential time, I will converge to that. Okay. So it means that the solution of this equation will go to equilibrium in a time of order log epsilon minus 1. In time of order log epsilon minus 1, I will just be very, very close. Whatever, no matter from where I start, I will be extremely close to the invariant measure. But the deterministic dynamics stay close for a time of order epsilon minus some power, some negative power of epsilon. So it's much longer than log epsilon minus 1. It means that indeed the deterministic dynamics will be close to the solution of this SDE for the time that it takes to this SDE to go to equilibrium. And so it means that the equilibrium distribution of this deterministic dynamics should be very close to the equilibrium distribution of this SDE. So this is okay. You can be happy about that. You say, ah, that's very nice. I understand what is the invariant measure of the deterministic dynamics. So I can control deterministic dynamics essentially for arbitrarily long time. But is this really true? Not really. Because think, for example, to a random walk in random environment. So no, sorry, in random walks. That's it. Forget that in normal random walk. But a random walk that makes jump of 2 steps. Okay. So it doesn't jump 1, but it jumps 2 steps. That's what it does. And it is 1/2, 1/2. These are jump 2 steps on the left or jump 2 steps on the right. And now you look, you rescale it, you look at it at the scale L, after a time L square, and what are you going to see? You are going to see essentially Gaussian. And then you see, you see, what I see is always a Gaussian. Yes, you always see the same Gaussian, no matter from what you start. But if you start from an even side, then you will be in an even side. If you start from an odd side, then you are supported on the odd sides, because the jumps are jumped by 2. So you cannot change, if you start from odd, you cannot change the parity. You will always be on odd side. So it means that, in fact, the distribution, if you really look closer, is not some nice, smooth Gaussian, but it's something that, you know, it is just supported either on the even or on the odd sides. So it is very wild. So in principle, something like that could happen here. Maybe if you look at it from far away, it looks like a Gaussian that is peaked around the attracting fixed point of the ED or the ODE, but then you look closer and you discover that it oscillates like crazy. So that is, and so there may be many of them that are all, from far away they look all the same, but you look close and they are all singular between each other, because they must be, and they intertwine in some complicated manner. So you don't really know exactly what the invariant measure looks like. And this is just one problem. Another problem is that, okay, I look at a very simple situation, a situation in which this vector field has only 2 zeros. What about if there are 4? If there are 4, 2 are stable, 2 are unstable. I put the noise, and now I have 2 stable. And what does this guy predict? This guy predicts that there is only one invariant measure. and it will be made of two Gaussian on the attracting fixed points, but the relative weight of these two Gaussian depend on the large deviation of this equation. That's what theory of Wechsler-Friendly say. And if imagine that you have a situation in which let me try if I can write something. Okay, disegno. So imagine that this is the vector field. Okay, so this is omega bar. And so you have this guy is a fixed point which is attracting, and this guy is a fixed point that is attracting. Okay, and now let's say that my initial condition is this one, but imagine that even color, that's fancy. Okay, so let's use green for the green for the Gaussian, that's okay. And now I have, let's say that this looks like the invariant measure looks like this. Okay, so this is almost a Gaussian, but the probability is very, very small, and the probability is almost 1 of being on this side. So if I start from here, this is my initial condition, what will happen? Well, it will happen that after some time I will see this distribution in green. And how long do I have to wait to see this distribution in green? Well, unfortunately, I have to wait a time that is of order e to the epsilon minus 1. And this is much, much, much longer than the time I can control. And I can say that the stochastic differential equation described is close to the true motion of the deterministic system. So in this case, I will be able to use this equation, because what happens that this equation exponentially fast will go to a situation that is a linear combination of two Gaussian, one here and one there, more or less. So there is essentially two-dimensional space in the space of measure, and I converge exponentially fast to this two-dimensional space. But then I get into this space and I get stuck. This is like a slow manifold. And there I move extremely slowly with this speed, and so I have no idea where I end up. And in fact, where I end up, it depends on the large deviation of the true system, the deterministic system. And the large deviation of the deterministic system are very different from the large deviation of this system, for the good reason that this is a Brownian motion, and Brownian motion at a certain point has very big kick, but the deterministic system has bounded kicks, because at each time you just can advance by some order epsilon. You cannot do some jump that is very large. So that means that if I look at large deviation for this process, they are completely different. The large deviation function is completely different. And so I cannot use my deterministic system to predict what will happen for a very long time in the deterministic system. Okay, that's annoying. Why it doesn't go? Because my fault, sorry. Okay. Did I? No. Oh. There, yeah. Okay. So the question is, okay, in order to understand what happened for very, very long times, for arbitrary long time, I need to understand what is the invariant measures of the system. And so this, as I argued, you cannot answer by averaging. You have to do something else. And so that maybe I want to say you what is a physical measure. The physical measure, because there is some difference between physical measure and SRB measure. In this particular case, they are the same. But this is a more interesting reason. The point is that physical measures are measures such that if you start with some initial condition x, and you take the trajectory and you take the average along the trajectory, then this average will converge to some measure. And point for which this average converges to a measure mu must have Lebesgue measure that is positive. So if this happens, then this is called the physical measure, meaning that you can see it, because you can look at what you do in an experiment. You see this thing, right? Because you have an observable, you apply this measure to the observable, and what do you get? You get just the average of the observable along the trajectory, starting with that initial condition x. And this tells you that you will see this average on a set of positive Lebesgue measures. So you have some actual chance of doing an experiment and see this as an average, right? So that's why people call it physical. And the point is that these physical measures are obtained essentially starting with the measure that is absolutely continuous with respect to Lebesgue, and then taking the average, right? So you take the push forward or pull back, I don't know, I'm unable to decide. And whatever, this thing with some, I think that the studies should really be down and not up. I think that is correct, but if it is a push forward or pull back, it's beyond me. In any case, I mean, this is the definition. And so you take the average of the observable, and with respect to this initial measure that is absolutely continuous with respect to Lebesgue. And if you take an accumulation point, then you will get some invariant measure. This is essentially Skriloff-Bogoliubov theorem. And that should give you, in principle, physical measures. The physical measures should arrive like this. And this is exactly what I'm doing in this example. I started with a measure that this is my hypothesis on the initial condition. I start with the measure that is absolutely continuous with respect to Lebesgue. So I expect to see physical measures. That's what I want to classify. What are the possible physical measures that I can see? Okay? All right, so there are quite a few results. Well, quite a few is exaggerated. There are few results on this subject. For example, there is this papers by Dolgopiat, Viana Young, Bonatti, Viana. But anyhow, these are very nice papers. But they have, all of them, they have a problem. And the problem is that in order to apply them, you need to know that the central Lyapunov exponent is either expanding or contracting. So what is the central Lyapunov exponent? You see, this system that I'm looking at, it has an expanding direction, and in that direction the Lyapunov exponent is positive because it gets expanded. And then it has a central direction. Central direction is, you can prove there exists a foliation made of closed curve, in this case, in which, which is invariant. And this foliation is the foliation in which is determined by the slow variable, in which things move very, very little, okay? Yet, you can have an exponent in this direction. Since there is an invariant foliation, you can take a tangent vector to this foliation and ask yourself, is it going to grow? Is it going to shrink? And the answer is that, this result apply if either you, in some technical sense, either you mostly shrink or you mostly expand. But the problem is that you have no idea how to determine if you shrink or you expand. This is actually the problem why I would like to have the invariant measure, to actually compute the Lyapunov exponent in the central direction. But this is just on the other. So I was very excited when I saw this result. I said, fine, the problem is solved. Then I try to apply them and say, I don't know. So, okay. And then there is another very nice result by Suji that says that for systems like the one that I described, generically, there is a finite number of SRB, of physical measures. But the problem is that I have a concrete system. Is it generic? I have no idea. So also this result, which is very nice, turned out to be not really applicable in concrete situations. So we did with Castorini some attempt of seeing if one can be a little bit more specific. And in fact, we could show that there are, for this system, there are, if epsilon is small enough, there are finitely many physical measures. And there is some technical condition on omega, which should not be homologous to a constant. But the point is that this condition is checkable. If you look at periodic orbit, you can check if omega satisfies or not this, so if this theorem is applicable or not. So this is a concrete theorem. You can actually apply it. So if you give me a system, I can check periodic orbit, and I tell you, yes, there are finitely many invariant measures. Okay. Problem is that finitely many, how many? We don't know. The result is not sharp enough to, because this measure actually we can prove that is in H1. Actually, so it's in Sobolev space H1. But the problem that I was telling you before, it could be that it oscillates a lot. So there are many that from far away they seem the same, but they are interlaced. So in order to avoid this, you have to show that the H1 norm is small enough, does not blow up too much. And we have an estimate for the H1 norm, but it blows up a little bit too much in order to conclude that there is, for example, only one invariant measure. Yeah?
You also have the exponential decay of correlation.
Yes, yes, you have exponential decay of correlation for each one, but you don't know how many. Yes, so it's nice result. I mean, but I should not say it. I'm an author, but anyhow, but still, does not solve the problem. And so there are a lot of open problems, but I think I'm over time, right? Yeah, sorry, I stopped.